definition, a first order differential equation where the right hand side does not contain the independent variable and is a function of just the dependent variable is called autonomous. So here are a few examples of autonomous equations. And if the right hand side contains the independent variable explicitly, then this is a non-autonomous equation. So of course, any autonomous equation is also separable. The important visual point about autonomous equation is that it can always be recognized by its direction field. In other words, by just looking at the direction field, you can always tell whether it comes from an autonomous equation or a non-autonomous differential equation. Well, the idea is that let me explain. So, if we have an autonomous differential equation, right? So y prime equals say f of y, and suppose we change t, right? So suppose that we change t to, I don't know, t plus some constant, say plus 2.5. Well, replacing t with t plus 2.5 is, well, it means, and if you apply this transformation to the graph of a function, then it means that the graph of your function is shifted 2.5 units to the left, right? It's like, so suppose that you have, say, I don't know, the graph of the function. Let me draw it, say, a parabola. Y equals t squared. Then if you replace t with t plus 2.5, then you will get another parabola that is different from the original parabola by moving 2.5 units to the left, right? So then this will be y equals t plus 2.5 squared, right? Because now if t is negative 2.5, then t plus 2.5 is 0, and then that's this apex of the parabola. Well, so generally speaking, there is this transformation. But if you look at the at an autonomous differential equation, then since it does not explicitly contain t, it means that if you change the current value of t to, well, t plus something or to t minus something, then the equation does not change. So it means that if you have any solution of the autonomous differential equation, then translating it to the right or to the left, you will get another solution. Right? So for example, if, say, I don't know, let me draw it like this. So if, say, this is a solution, then just translating it by to the right, we're still going to get a solution. And translating it to the left, we still are going to get a solution. Well, but then geometrically, it means, it also means the following. It means that if we look at, say, well, all the vectors of the direction field for a fixed value of y, then the direction of the vector does not depend on t. So which means that for a fixed value of y, all these vectors are going to be exactly the same. Or, for example, I don't know, all these vectors are going to be exactly the same, and so on. So if you trace vectors along any horizontal line, then they are all exactly the same. So if this property holds, then the differential the corresponding differential equation is autonomous. If this property does not hold, then the differential equation is not autonomous. So here is another example. So these differential equations are non-autonomous, right? Because if, say, I don't know, if say you look at this particular value of y, then say vector at this point is different from the vector at this point, is different from the vector at this point, and so on. And same thing here, right? So if you look any kind of row of vectors, then they're different. So here it's almost horizontal, and here it's a bit steep. And so the angle is 45 degrees.